Hello dear students. So this is another lecture on this complex analysis, and in this lecture we are going to discuss about how to solve the different kinds of integrals. Maybe in our previous lecture, if you remember that, so you can visit my lectures also. We have talked about how to solve these proper or improper integrals. Like if we have integration from some limit a to b, right? So we can solve those integrals on this complex plane. And in addition to that, if we have some these integrals where the limits goes from minus infinity to plus infinity, right? So in that case, we can also solve those integrals over the semicircle, and those are basically improper integrals. So today's topic is that is we want to prove that we have to prove that for if a is greater than 0, so that means the value of this a should be greater than 0. So we need to prove that 0 to infinity cos of x d of x divided by a square minus x square equal to this thing, right? So ये हमें prove करना है, so that means we need to prove it over the semi-half circle, right? So that means so first of all, so if you remember that, because we have it is basically a kind of Fourier integral here. We have some f of x or that complex function or f of z, right? So this, that basically lies in the complex plane. And in addition to that, we have these cosine terms, or it can be sine term also. So that means first of all we need to write. So we need to write that cosine term, or it can be sine term. So we need to write it in the exponential form, right? So first of all, because if you remember in my previous topic we have talked about this. So let's write first. So we can rewrite this integral. So let us write that I equal to, that is Rosary integral cos of x. So these are closed contours, right? So that means our integration, or you can, okay, let me put it here like this. So our this integration is from, so this is from minus r to plus r, and this is s, right? And this basically indicates the closed contour. So that means that closed contour, it includes both these integrals. So one is coming from this curve S, and another is coming from this real axis, right? So that goes from minus r to plus r, right? So first of all, so we're saying that our integral, so that means this integral can go from some minus infinity to plus infinity, right? Because when you put r turns to infinity, right? Or this time you can say that it is going from minus r to plus r, right? But if you put that r turns to infinity, or this the integral which is above the semicircle, so that will be equal to 0, because this curve it basically lie on these real axes at that point. So that means we can only one integral that's coming from this minus r to plus r, and the integral from this comes out to be 0, right? So before that, so if you remember that in so firstly let's write that cosine term in terms of that exponential form, and we need to check whether it's the real or imaginary part of that, right? So I can rewrite this integral as, so I can write this as I will be equal to, so that's equal to, okay, so let's write, because it lies in the complex place, so let's write it z here. Okay, so that is iota z. Because it's very clear, because if you expand this term, अगर एक term हम expand करेंगे, so that means cos of iota z, or you can plus, okay. So that means if you expand this term, that's e power iota z is basically this cos z plus iota sin z. So that means this first term, that is cosine of z. So it is basically the real part of that. So इसका real part है. So that's clear. So that is what I wrote here. That RE, it stands for the real value of this exponential function and divided by the same term that we have. And in addition to that we have this, right? Okay, so this is very clear. So what I did here, so this is, or you can write this I equal to real part of that, this e power iota z, right? Or you can write this as, you can take that real out. So this will integrate e power iota z, a square minus z square into dz, right? Or you can, instead of that, So this will be equal to that. Okay, so that's our I dash. So first let us solve this integral I dash, and then we can write that using that Cauchy integral, Cauchy residue theorem. So we'll do it later, right? So first let's solve this integral, the I prime. So I prime is that, right? So that means, right? So this is power iota as a square minus z square, right? Okay, so first, if you want, because our absurd is that's our analytic function, and we need to check the poles for this function absurd. So whether they lie on the real axis or they lie above the real axis, that will lie within this semicircle, right? So we need to check it first, because so then accordingly we can calculate the residue at those points where our singularity lies. So first let us check the poles for this function absurd, right? So we can write that. So that means we have this k square. Right? So it has two poles. So one lies at plus a, because if you remember that, तो आपको पता होगा कि मैंने already यहाँ पे लिखा है that if a is greater than 0, so that means a value it can be 1, 2 or 3, right? So it 1 unit, 2 unit is above this real axis, right? Because so that means we have two poles. So two poles. So one lies above the real axis and one lies below the real axis, right? So that means we have this kind of this. Or you can put it like this. So this is our semicircle of S. It goes from minus R to plus R, and we have one pole at minus A here and another pole here. Okay. So that means, so यहाँ पे हमें देखना है कि जो A होगा, so okay, sorry, so I did a mistake here. Sorry. I should put it like this. So it can be here. One is here minus A, and this is, so that means we have two poles. So because it is plus a and minus a, so plus a it lies on the real axis. So that means both the poles of for this function absurd. So they lie on the real axis, right? Because one pole is here at z equal to a, and another pole is when z equal to minus a, right? So that means we can now solve this. We can compute the residue. So we can compute the residue at these two poles at z equal to a and z equal to minus a, right? So let's compute these poles for this function, because there is no residue, no pole which lies above this within or on the semicircle, right? So that means the contribution from this, so this will be 0, right? So only the contribution will be from this line, the real axis which goes from minus r to plus r, right? So that means I can rewrite here. So that means I can write here the residue of this f of z at z equal to a. Okay, so let me write one more step because there is minus sign here. Huh? So let me check it. Where this is z minus a. Okay, because so what I did here. So यहाँ पे मैंने simply that our f of z was e raised parameter z divided by z minus z into a plus z. So that's clear. Huh? Okay. So so that means we can rewrite this term as because this will cancel. So you have minus sign here because this is z minus a and this a minus z. So we can have minus sign that you can take outside this integral, and we can write this as minus, right? So this is coming from the residue of this f of z, right? And in addition to that, we can have one more that this residue because that lies at z equal to minus a, right? So we can compute the residue at this pole also, right? So that means we can rewrite this as residue of this f of z. Okay, or you can write this as okay because this a plus z it will cancel with this thing. Okay, so we can have because our z tends to minus a, so this is minus. Sorry, and this okay, so this is a plus z will cancel, so that is minus a, it will be 2a. Right? So this is clear because your z is tending to minus a, so it will be e raised power minus iota a, and this a plus z and z plus a will cancel, and this will be a plus a, so that's twice a. So this is what I get from here. Okay, so that means we have two poles. So that means so first one is that is z equal to plus a and z equal to minus a, right? So that means if you remember that, so in class I have discussed that if you write this integral, if you put that, so you can write that I will be equal to that is equal to first let us write that imaginary part of that I dash. Right? So just check so whether this is correct. So why I wrote that. Okay, so okay, where is that? Okay, this one. Okay, because okay this one because I prime is basically this one, right? So that means पहले हम I prime लिखेंगे that is basically real part of this. Okay, real of I prime. So that means इसके बदले में लिख सकता हूँ that is real prime of this real value of this I prime. Huh? So this I can write as okay so either we have to write it this way or okay so first okay, so let's write that. Okay, so that's clear. Before that let's write this. Okay. So this is clear because first let me write the contribution from here. Okay. So because we have this integral that is going from 0 to that 0 to s e power iota z, right? Because so this is what I did here. So I'm basically taking this integral over this curve semicircle, right? So that goes from some 0 to 0 to s. It's a closed curve, right? It is from or you can it goes from some minus r to plus r. You can write this here, and over this curve s, right? And this is equal to, if you calculate this, if you calculate this integral over the semicircle, so that will be equal to, according to that Cauchy residue theorem, so that is equal to 2 pi I times the sum of the residues, right? So यहाँ पे जो residue होंगे, जो poles होंगे, वहाँ पे हमें compute residue करना है. The poles which can lie within this region or which lie on this semicircle, right? So we can compute residue at those points. But as per our the integral, the function that we have, so it doesn't have any poles on this within this semicircle or on the semicircle, right? So that means the total residues, total poles that lie within this on this semicircle is zero. So that means I can write this as, so this integral will be equal to, so we can write that minus infinity to plus infinity. So we can write this way. So that's equal to, so that means there is no contribution from it, right? Because our integral was, if you remember that, our integral was from minus r to plus r. F of z is plus integral over this s f of z is, so that is equal to pi times plus, right? So this way, because that is equal to, this comes from the semicircle, जो semicircular circle है, उसका आएगा 2 pi I times this thing, and from this real axis, so that is iota pi times this thing. Okay, so that means, because when you put that r tends to infinity, right, so this will be from minus infinity to plus infinity, right? So that is f of z dz. So that's equal to, and first one will be zero because there is no pole which lie within this semicircle or on the semicircle. So the contribution from this first term, that's equal to zero. Only we have second term here, right? And second term basically gives us that's iota pi times. That's what are the residues? So residues basically that is, so just check here. So residue पहला था, so that was from here, that's e raised power. So first let's write this term. So that's minus e raised power iota pi by a. So I can rewrite this as minus e power iota a by 2a plus e power minus iota a by 2, right? So इसको मैं ऐसे भी लिख सकता हूँ, or you can take that 2 by out, right? And so this will be equal to, okay, so that will be equal to, right? Because I can write that minus iota when I put it in the denominator, so it will be plus, right? Because we have minus iota in the numerator, so it will become plus iota in the denominator. And this term I can write, so you can write that 2 iota inside that bracket, and we have this term. So this is simply that sine term. It's called sine of x, because that sine of x equal to, that's e power iota x, and cos of x equal to, right? So you can check that. So whether it is plus or minus, you just check. Huh? So because we need only this thing, huh? So there is no need to take this because we have only the sine term. So this is this. So you can check also for the cosine term. So that's e raised power iota x plus e raised power minus iota x divided by 2, right? So because this is our sine x, right? So this will be equal to sine of x. So that's equal to, so if we check that, so we need to take the real value of this, because when you compute the residue, तो यहाँ पे आपको क्या करना है, आपको इसका रियल वैल्यू लेना है, राइट। तो रियल वैल्यू इसका क्या होगा, सो दैट मीन्स यू टेक और यू कैन पुट इट लाइक दिस, ओके। सो लेट मी राइट वन मोर स्टेप, so I can put this as the real value of that pi by a, so that's equal to pi by a sin of a. तो इसको मैं ऐसे भी लिख सकता हूँ, राइट। And because okay, so we can rewrite this term because we already observed equal to, that's from minus infinity to plus infinity. So you write that it is that cosine of z, cosine of x upon that a square minus x square d of x. So that's equal to pi by a sine of, right. Now we have this, because this is an even function. You can, when you change that, when you shift that x to minus x, so this is an even function. So you can write this integral as from 0 to infinity twice, right. तो इसको मैं लिख सकता हूँ, I can rewrite this integral as from 0 to infinity cosine of x upon a square minus x square d of x equal to pi by 2a. So that's what I need here. So just check. So what was our result? So we need to prove that it's equal to, okay, so that's equal to okay, so that's equal to pi by 2a sine of. So that's what we get here. So that's equal to this. Okay, that's pi by, that's equal to this pi by 2a sine of, because where, because our this function is this cosine of x is going to be a square minus x square. That's our it's an even function. We can write that's equal to twice that integral, right. So this is what we get here. Or there's another way, you can also take the different these integrals, right. Like if we have, so let's, so we can elaborate it like this. So we can have so we can elaborate, because if you remember that our function was, it has two poles, one lies at z equal to plus a and another lies at z equal to minus a, right. So that means we have two poles here. So we have this semicircle here, right, and we have two poles here. So one lies at minus a and another lies at plus, okay. And this is semicircle, okay. This is semicircle and this is gamma 1 and this is gamma, right. So the function goes like this, right? So we have two poles now. So I'm basically, we can handle it this way also. So we can do it another way also, right? So first is that, if you remember that our this integral is, so first integral, if you take the integral over this semicircle, right? So according to that Cauchy residue theorem, I'm repeating that, I'm revising that, that integral over that semicircle, that's 2 pi I times that sum of residues, because we don't have any residues, any poles which lie within that semicircle or on the semicircle. So that means the contribution from this semicircle, that will be equal to 0. And only contribution comes from these poles which lie on the real axis, that z equal to plus a and z equal to minus a, right. So this is what we get here. So we can write that. So we have these two circles, that is R1 and R2, and this I can write, this will be equal to, because this will be minus R1 to plus R1, and second is this is minus R2 to plus R. Okay. Now I take the all the integrals that are present here. So first integral is from that over the semicircle, another integral is from this point to the circle, because this R is tending to 0 here, right? So that means another integral is from this point to that point, from A to then this point, then so we have 5 or 6 integrals here, right? So let us write one by one. So I can write, so first integral will be equal to, that's equal to from minus R, so that will be from minus R, because this is minus R to plus R. Right? So this is our real axis. So I'm not showing this, so this is our real axis. Huh? Real axis. Okay. So that means, so first जो integral limit आएगा, so it will be from minus R to up to this point A, which lies in the neighborhood of this pole, right? So that will be from minus R to that will be minus R to minus R1 plus R. right? So what I am doing here, so if you check that, तो यहाँ पे मैं क्या कर रहा हूँ, so पहला जो इंटीग्रल आएगा ये आएगा इस पॉइंट से लेके from this minus r to near to this, because we have that minus r1 minus a, that is minus times r1 plus a, so that's up to this point. Okay, right. Because the circle is very small, so it's close to that point a, right? And the second integral, so this is first integral, so it will be that f of x dx plus, so ये हमारा first integral है, so second integral will be from this point to this point, so that means the second integral will be, or we can take, okay, so you take one more integral, so okay, so that is one more integral will be r1, that's f of z dz. So first integral is from this to this point, another is this over this r1, right? So that's above this above the real axis. So this is our semicircle here, right? So this one r1. So that is that's why I wrote here f of z dz, because it can have both this real as well as the complex part. But you know, first integral I'm writing only the real part. That's f of x. Right? So this is clear. So this basically comes from here, and similarly another integral will be from, that will be from this point, from minus a plus this term to this, right? So that means another integral will be from, that will be, you can write this as r1 to a minus r. So that means another integral is from this point. So in the close of this, so that means minus a. So just check. So there's some. Okay, so let me first stop. Okay, so this clear. So another integral कहाँ से आएगा? So it will come from this minus a plus r, और जिसको मैं ऐसे भी लिख सकता हूँ. It is basically minus a plus r. So that is minus, you can take out minus a minus r to a minus r2. A minus r2 is basically which lie in the neighborhood of this point. So that is our, that's a minus r2, this point. So but this will be our f of x dx plus, and another integral you can take from, so that will be over this r2 f of z dx plus, and one more integral will be from this point, means a plus r2 to this point. So that is over that plus r, huh? Okay, plus r, right? So that should be equal to 0, because the compute is basically horizontal closed contour, so that should be equal to 0, right? So that means we have these, all these contributions. The integral is, so पहला जो integral होगा from minus r to this point, then another way over the semicircle that comes from here. Okay, let me repeat it here. So पहला ये वाला integral इस point से लेके यहाँ तक है, that is minus r to minus r1 plus a, because both are minus. So this is minus r1 minus a, or you can write minus into r1 plus a. It will be that f of x dx, right? So ये हमारा दूसरा integral होगा over this r1, so that is this one f the dz, right? And another integral will be from minus a plus r1, that's minus a, or you can take minus into a minus r1 to a minus r2, because it will come up to this point, right? So that will be this one, f of x dx, and then over a semicircle, so that is r2 f of z dz. And the last one will be from this point. So ये जो हमारा है, that is a plus r2, a plus r2 to plus r f of x dx. And another, that is basically over the semicircle that comes from this. So that's our semicircle, that's f of z dz. So that means the contribution comes from all those integrals, and we can put some approximation that, so two approximation where we put here two approximation. First approximation that when you put r tends to 0, and similarly when our small r1 and r2 tends to 0, because अगर ये close, ये point close होगा इसके, right? When it tends to 0, so that it is approaching to point A, the pole at minus A. And similarly when you put r2 equal, r2 tends to 0, so this is approaching to the another pole which lies at z equal to plus a. So that means in that case, that limiting case, and one more that one more approximation, we are saying that if our r tends to infinity. So that means the contribution from this semicircle will go to 0, right? So taking all those, so we can get the same result. So this is okay. So in our coming lectures, hopefully I will solve one more problem, but using this method, right? So this is the same method, but I am basically splitting it. I am not using that. Finally, I am computing the residue, but I am writing it in the integral form. So the contribution from all these integrals which comes due to this real axis plus that semicircle, right? So put by in addition to that, by putting those approximations, so those are there, that r1 r2, that semicircle those tends to 0, and that r tends to 0, right? We will get the same result. So hopefully in our coming lecture I will take one or two problems, but using this procedure, and so it will be helpful for you.